Welcome to the ultimate Solidity Smart Contract Web3 Blockchain Developer course, Foundry Edition. Previously, we've done two other massive courses and tutorials like this, one of them with JavaScript and one of them with Python, and then now one in pure Solidity. And combined, those two videos have over 5 million views, making them the most watched blockchain developer educational material on the planet. And we're looking to do it all over again. We've learned a ton from making those first two courses, and we've taken all of those learnings from those two courses, wrapped them up into this one to make this one the best one yet. If you're more interested in full stack development and working with JavaScript, the Hard Hat one is still a phenomenal resource for you to get started. However, this one has a ton of advancements in it, making it the most cutting edge Web3 developer course, period. Having done one of these videos every year for the past 3 years, I've been reached out to by countless developers who are now full-time developers in the Web3 space, making a living, doing well, and contributing to Web3. And there are thousands that I have not met who have left comments or left me notes, and I know we're gonna do it again with this video. If you're looking to become a Web3, Solidity, smart contract, or blockchain developer, or any of those terms, this is the course for you. And this course is for anybody and everybody, no matter your blockchain or developer experience level. And additionally, we're going to be using artificial intelligence to accelerate our learning progress. And I'm going to teach you not only how to become a blockchain developer, but how to work with AI tools to make you a 10x developer. If you have a little bit of developer experience before this course will be even easier to get through. But again, don't worry if you've never coded before. And for those of you who are already familiar with blockchain and smart contract development, feel free to jump around the different modules and different sections and grab the learnings that you want. I promise there's a lot of cutting edge information in here, and maybe you need to brush up. So no matter if you're brand new to coding, brand new to blockchain, or you're an experienced smart contract engineer, you're in the right place. Welcome to the edge of the rabbit hole. Let's get froggy. For those of you who don't know me, my name is Patrick Collins. I'm a smart contract engineer, security researcher, and just lover of all things Web3. I'm one of the co-founders of the smart contract auditing firm, Cyphren, avid smart contract YouTuber, co-creator of Web3Education.dev, and I live and breathe smart contract development. I absolutely love Web3, blockchain, and smart contracts, and I love the power and the tools that they enable us to use. But not only that, I love taking blockchain developers like yourself watching this video right now on the journey to becoming a successful smart contract developer. I think the key to Web3, to blockchain, to cryptocurrencies being successful is having a phenomenal foundation of developers. So I'm incredibly excited that you're here with me. And for those of you who don't want to become blockchain developers, the first two lessons of this course, lesson 0 and lesson 1, are foundational pieces of conceptual information for you just to understand how to get into this Web3 thing. So if you don't want to become a developer, just stop once we get to the coding. For my Pythonistas here, I'm working on an edition of this course purely in Python and Viper. Stay tuned for that as well. In any case, I'm incredibly excited for your journey. This is a data dump passion project of all the knowledge that I've collected over the past few years of working in this industry and being a smart contract developer myself. And at this point, I have the track record to show that I am 100% confident that if you follow along, if you code along with us, if you follow me on this journey, you will come out the other side armed with the knowledge to be a positive force for the cryptocurrency and blockchain industry. Smart contract and Solidity developers are massively in demand, with an average salary being around $145,000 a year. And with AI coming in place, it's becoming even easier to get up to speed quickly. But only those that understand the technology truly will be able to take advantage of all these advancements. AIs get stuff wrong a lot. So we especially need the knowledge to fact check whenever AIs get things wrong. Being here, you have the opportunity to be a pioneer, ushering in the age of Web3, of cryptocurrency, blazing the trail of where this phenomenal industry has yet to go. Like I said, this isn't the first time we've done this. We've already helped so many developers get into space, and we're gonna give you the cutting edge, most modern tools for industries like DeFi, NFTs, DAOs, tokens, upgradable smart contracts, blockchains, and everything else that you can think of. Once you finish this course, it will be abundantly clear what you want your next steps to be. And you'll have a ton of economic opportunity at your fingertips and opportunities to make a huge difference in this amazing industry. However, I can't just give it to you. You have to come with me on this journey. You have to take the step. Despite what you might think you know, cryptocurrencies and smart contracts enable a more accountable world, a more transparent world, a more collaborative world, a world where promises can't be broken. And that's a world that I want to live in. We'll learn more about the purpose of smart contracts and the purpose of blockchain technology in lesson 1 of this course. And then of course, we'll teach you how to build it. So before we even get started, I want to give you a huge thank you for even being here on this video and listening and being interested in engaging in this phenomenal technology. So thank you for being here and welcome to the rabbit hole because we're about to drop down. With that being said, let's get froggy. So let's begin our journey by talking about some best practices. That way you can get the absolute most out of this course and be as effective as possible. Now, there are 2 links in the description that I want you to pause the video right now, go into the description and click on and open up. The first one is web3education.dev, and the second one is a GitHub link to a repo, also known as a repository, with all the code and all the lessons and everything we're going to be covering in this video. The web3education.dev site is an education site that we're working on to have all of this video and everything else and all the cutting edge learnings of blockchain developers in this course, in this site. So if you enjoy written context as well, be sure to subscribe to sign up for that so that you can be one of the first people to know when it launches. And the second site is this GitHub link. This is going to be your Bible for the duration of watching this video. It has everything that we're going to go over. It has all the code, context, text, etc. that you're going to need to be successful in this video. And I'm going to be referring to it pretty often as we go through the course. Additionally, in this GitHub, there's a discussions tab right here that you can click on. And in here is where you can ask questions, discuss with other people taking the course, interact with members helping out, and it's where you can discuss anything that you're having trouble with. And an important note, sometimes you'll see this as the chainxl.org Foundry Full Course. We recently renamed it to the Cyphren Foundry Full Course. So this is the correct link, but if you see chainxl.org, that's fine as well. That being said, as we go through this course, we're also going to teach you some best practices on working with artificial intelligence, how to best prompt these AI so that they can give you the best results. Just keep in mind, they sometimes get things wrong. And it's a good idea if you are going to use an AI to fact check it with a human or another resource. So be sure to say hi in the discussions and maybe meet some like-minded peers. And additionally, once we do get to the coding portion of this course, it's a good idea to code along with me as I'm explaining things. So having the video up as well as your coding screen is a good idea so you can follow along with me as I'm explaining it. Now, this space moves incredibly quickly. So whenever I open some documentation or some code base or something, I highly recommend that you open it as well in your browser, just so that you can know immediately right away that the code that I'm working with in the video is going to be the same that the code that you're working with locally. Now we're going to be keeping all of the code in here up to date, but sometimes things change and something that I do in the video might not be the most up-to-date best practice. So we're going to have this file called chronologicalupdates.md where you can go in and check to make sure that you're working on the most up-to-date edition. So if you go into that file, each lesson will have a section, and if there's some update that we made to the lesson, you can find it in there. Additionally, if you think you found something that is different or doesn't quite work, be sure to make a discussion for it in that GitHub repo. Like I said, it's going to be your Bible. But yes, if you run into an issue, make sure that file is one of the first places that you check just to make sure that all the code that you're working with is the most up to date. All of this is to say, if you run into an issue, jump to that GitHub repo and make a discussion. We will also be giving you some tips very soon about how to best make a discussion. Yes, asking questions to other human beings is a skill. And we're going to try to teach you to be the most effective because asking well-formatted questions is not only the secret to being a fantastic AI prompt engineer, but also becoming an incredibly successful developer. We're going to learn how to ask well-formatted questions. And whenever we post on discussions or forums or whatever, we're going to work on formatting them as best as possible. Take breaks. I cannot tell you how many people have tried to rush through these courses and be like, oh, I'm going to finish in a single weekend. Your brain doesn't work like that. Your brain needs time to absorb the information. So take breaks. Maybe every 25 minutes to a half hour, take a 5-minute break. Or maybe you like working in longer chunks. Maybe take a whole hour and then take a 15-20-minute break. Don't try to rush through the whole video in a day. You're not going to retain the information. Go outside, go for a walk, grab some ice cream, get some coffee, go to the gym. Your brain needs time to have the information settle. Maybe every 2 hours, just step away, maybe be done for the day. Work at whatever pace makes sense for you. Everyone's going to have a different learning pace. There is no right speed for this course. I've had people take my courses in 2 weeks, in 3 months, in 6 months. It doesn't matter. Pick a pace that you can do and stick to it. Not only work at your pace, make sure that I'm talking at a pace that makes sense for you. There's a little gear icon in the YouTube video here where you can change the speed of how I'm talking and how fast the video is going. So if I'm talking way too fast for you, then you can slow me down. But if I'm talking too slow, then you can speed me up. So make the adjustments you need to make me go the speed you want me to go. Now, a giant video like this can be kind of hard to triage where you left off. So using the GitHub repo with the timestamps in there is a good way to say, okay, I was on lesson 1. Let's click the link there to jump right to the timestamp. If you pause a video in YouTube, you can actually right click and say, copy at current time, and maybe drop that into a notes folder somewhere so that you can always just pick right back up where you left off. Or like I said, you can use some of the timestamps in the GitHub repo associated with this course. Or depending on when you watch this, the web3education.dev site might also be up. Be sure to check that out as well. And of course, this course is modular, so you can bounce around topic to topic and go to where you want to go. If you don't want to do any full stack stuff, then skip that section. If you want to go right to the advanced stuff, do that. Like I said, go the pace and take the learnings that you want to do. And after every lesson, it might be a good idea to go back and reflect on each lesson to really make sure the knowledge gets ingrained. Repetition is the mother of skill, and we're going to be repeating a lot of smart contract development. Now, additionally, at the end of every lesson, you'll see a little QR code that looks something like this. And there will be a link in the GitHub repo pointing to the same place that this QR code is pointing to. These are optional challenges that you can do to try to make sure that you actually learned what was meant to be learned here. And if you do solve them, you get a very cool NFT along with it. Don't know what an NFT is? Don't worry, we'll teach you later. Blockchain development and open source development world is incredibly collaborative. So be sure to use tools like, of course, the GitHub Discussions tab, Ethereum Stack Exchange, the decentralized Q&A forum, Piranha, issues on different GitHubs, artificial intelligence, and more. And like I said, we'll give you more tips on how to most effectively use these sites in the future. And the reason I'm putting so much emphasis on this, and that I will continue to put so much emphasis on this, is being a successful smart contract developer is more than just knowing how Solidity works. Knowing where to go for information and how to collaborate with people is often more important than your smart contract knowledge, because oftentimes you're going to run into issues you don't know how to solve. So we're going to teach you to unblock yourself on this and really anything in life. Plus, syncing with other people in the space makes it way more fun. Now, before we can actually get to coding, we need to understand how the blockchain even works, what the purpose of these smart contracts even are. And this is essential to becoming a successful smart contract developer, because a technology is really just a solution, and a solution is only as good as the problem is. So we need to make sure we understand the problem really well so we know how to attack it with this smart contract technology. And the better you understand the smart contract technology, the better you'll be able to architect your smart contracts in the future and make really intelligent, really powerful systems that further this amazing industry. But if you already know the basics of blockchain, feel free to jump into lesson 2 and skip over lesson 1. So those are some of the best practices to be really successful with this course. But with that knowledge, you're now standing at the edge of the rabbit hole. And if you're like me, once you jump in, you'll just want to keep going deeper and deeper. I'm so excited for you to embark on this journey with us. And I'm looking forward to seeing you on the other side, just like the thousands of other developers who have taken these courses and have emerged the other side triumphant. So it all starts with blockchain basics. Let's get froggy. Now, since you're here, you've probably heard of Bitcoin before. Bitcoin was one of the first protocols to use this revolutionary technology called blockchain. The Bitcoin white paper was created by the pseudo-anonymous Satoshi Nakamoto, and it outlined how Bitcoin could make peer-to-peer transactions in a decentralized network. This network was powered by cryptography and decentrality, and it allowed people to engage in censorship-resistant finance in a decentralized manner. Due to its features, which we'll talk about in a little bit, people took to this as a superior digital store of value, a better store of value over something like gold, for example. And that's why you'll also hear people commonly refer to it as a digital gold. Similar to gold, there's a scarce amount or a set amount of Bitcoin available on the planet. only so much that you can buy and sell. You can read more about the original vision in the white paper. We have a link to the white paper in the GitHub repo associated with this course. Now, this was an insane breakthrough. And in a little bit, we're going to learn exactly how this is all possible and how this actually works under the hood. Some people, though, saw this technology and wanted to take it a little bit farther and do even more with this blockchain technology. And a few years later, a man named Vitalik Buterin released a white paper for a new protocol named Ethereum, which used this same blockchain infrastructure with an additional feature. And in 2015, him and a number of other co-founders released the project Ethereum, where people could not only make decentralized transactions, but decentralized agreements, decentralized organizations, and all these other ways to interact with each other without a centralized intermediary or centralized governing force. Basically, their idea was to take this thing that made Bitcoin so great and add decentralized agreements to it, or smart contracts. And in fact, technically, these smart contracts weren't even really a new idea. Back in 1994, a man named Nick Szabo had actually originally come up with the idea. Smart contracts are a set of instructions executed in a decentralized autonomous way without the need for a third party or centralized body to run them. And they come to life on these blockchains or these smart contract platforms like Ethereum. And it's these smart contracts that are going to be the core thing that we're going to be working on in this course and that we're going to be developing. You can think of smart contracts in the same way you think of traditional contracts or traditional agreements. They're just a set of instructions between parties. Except instead of written on pen and paper or typed up in Microsoft Word, they are written in code and embodied on these decentralized blockchain platforms. And that's also where they're executed, instead of being executed by the 2 parties or 3 parties or however many parties that are involved. This removes this centralized issue that we'll talk about more in a bit. This is one of the main differentiators between the Ethereum protocol and the Bitcoin protocol. It's these smart contracts. Now, technically, Bitcoin does have smart contracts, but they're intentionally Turing incomplete, which means they don't have all the functionality that a programming language would give them. This was an intentional move by Bitcoin developers. Bitcoin developers viewed Bitcoin as a store of value, versus Ethereum developers viewed Ethereum as both a store of value and a utility to facilitate these decentralized agreements. Now, these smart contracts on blockchains alone are absolutely incredible. However, they do come with a huge issue. If we want these digital agreements to replace the agreements in our everyday lives, they probably are going to need data from the real world. Blockchains by themselves actually can't interact with and can't read or listen to data from the real world. This is what's known as the Oracle problem. These blockchains are deterministic systems, and they're deterministic on purpose. And we'll learn more about how that works in the sessions to come. So everything that happens with them happens in their little world. But if they're going to be these agreements, they need external data and they need external computation. And this is where oracles come into play. Oracles are any device that delivers data to these decentralized blockchain or runs external computation. However, if we want our applications to stay truly decentralized, we can't work with a single oracle or a single data provider or a single source that's running these external computations. So we need a decentralized Oracle network similar to our decentralized blockchain network. Your on-chain logic will be decentralized, but you also need your off-chain data and computation to be decentralized. Combining this on-chain decentralized logic with this off-chain decentralized data and decentralized computation gives rise to something called hybrid smart contracts. And most of the biggest protocols that we interact with today are some type of hybrid smart contract, or interact with hybrid smart contracts to some extent. This is where the protocol Chainlink comes into play. It is a modular, decentralized Oracle network that can both bring external data and external computation into our smart contracts to make sure they're decentralized end-to-end while giving them the feature richness that we need for our agreements. Chainlink allows for us to get data, do upkeeps, get random numbers, or really customize our smart contracts in any meaningful way. Now, throughout the course, we're going to use the terminology smart contract. However, whenever we say smart contract, we're often using it a little interchangeably with hybrid smart contracts. But just know that when we say hybrid smart contract, we're talking specifically about smart contracts that have some type of off-chain component. Now, since Ethereum's release, a number of different blockchains or smart contract platforms have come to light, such as Avalanche, Polygon, Phantom, Harmony, and more. For the majority of this course, we're going to be assuming that we're going to be deploying to the Ethereum network. However, everything that we learn here is going to be applicable to the vast majority of the blockchains out there, like Polygon, Avalanche, Phantom, Harmony, etc. And understanding everything from Ethereum fundamentals will give you the skills that you need to switch chains very easily with literally one line of code. So don't worry about learning a specific tool or with a specific chain, because most of them work together seamlessly. Now, there are a couple of smart contract platforms that don't use Solidity, but still learning the fundamentals here will make you much better at those as well. And Ethereum by far has the most value locked and is the most used blockchain and smart contract platform out there. You'll also hear those two terms used a little bit interchangeably as well. Sometimes I'll say smart contract platform, sometimes I'll say blockchain. They kind of mean the same thing. Obviously, blockchains could mean store of value and smart contract platform, but you get the idea. Similarly, Chainlink is the most popular and powerful decentralized Oracle network, is the one that we're going to be focusing on for this course as well. Chainlink is also blockchain agnostic, so it'll work on Ethereum, Avalanche, Polygon, Solana, or really any other blockchain out there. Now, additionally, over the last year, a new term has come to light called an L2 or a layer 2. This solves an issue that most blockchains see where they don't scale very well, or they don't grow big very well. We'll be talking about L2s a little bit more in the future, but the basic concept of it is that blockchains can really only get so big. So what they do, if this is Ethereum, you can actually have blockchains hook into them to essentially make them bigger. If that doesn't really make too much sense, don't worry about it for right now. Layer 2s solve this scalability issues. And at the moment, there are two different types of true layer 2s, optimistic rollups and zero knowledge rollups. Optimistic rollups like Arbitrum and Optimism, or zero knowledge rollups like ZK Sync or Polygon ZK EVM. Yes, there's a Polygon chain, but there's also a Polygon ZK EVM L2. The two of them are very different. Don't worry about them for now. And in fact, it's this Arbitrum layer 2 where our challenge contracts are going to be deployed on this rollup. But like I said, once we learn how blockchains work from a basic level under the hood, then we'll explain more about how these L2s actually work. Now, throughout this course, you'll hear the term DApp, or decentralized protocol, or smart contract protocol, or decentralized application, and they all kind of mean the same thing. A decentralized application is usually the combination of many smart contracts. And when we get into Solidity, you'll see what a singular smart contract really looks like. And like I said, learning all these core fundamentals will make you a better Solidity and a better smart contract developer. You'll also hear the term Web3 a lot in this video and in the industry. Web3 is the idea that blockchains and smart contracts are the next iteration of the web. Web 1 being this permissionless open source world with static content. Web 2 being the permissioned web with dynamic content. But all the agreements and logic runs off of centralized servers where they control your information. And then Web 3 comes back to the permissionless web, but once again with dynamic content. And instead of centralized servers running your logic, decentralized networks run the logic, creating these censorship-resistant agreements that these smart contracts enable. It is also generally accompanied by the idea that the users own the protocols that they work with, and it's an ownership economy. You'll see what I mean later in this course. Now, we've talked a lot about the history and about the high level of these protocols and of these smart contracts and what they can do. But what do these smart contracts really mean? What is it when I say trust minimized agreements or unbreakable promises? What is the real value add of these smart contracts? Before we look under the hood and take a peek at how this all works from a technical standpoint, let's learn what all the value of this is. What is the purpose of us building all these technologies, of you taking this course? What problem does this technology solve? In my mind, a technology is really only as good as the problem that it solves. If it doesn't solve a problem, then why bother? Smart contracts, blockchain, Web3, cryptocurrencies, those are all just different words that encapsulate the idea of what we're doing in such a unique paradigm. I think the easiest way to sum up what these smart contracts do is that they create trust minimized agreements. And if you might be scratching your head to that, a much easier way to think about it is just they give rise to unbreakable promises. Yes, you heard that right. Unbreakable agreements and promises. Additionally, they give rise to speed, efficiency, and transparency, and a number of other things. I made a video pretty recently about exactly this. So let's dive in and take a listen to the purpose, the undeniable value of smart contracts. Cryptocurrencies fundamentally re-landscape markets and agreements as we know them. Unfortunately, you've probably only been bombarded with people screaming about NFTs and money. Now, some of the memes are fun, but let's forget the bullshit and get down to the essence of this space. If you're already in Web3, this is the video to send to your friends to explain why you're so excited about this space and explain why we're here. And then if you're not into crypto, you've come to the right place. And yes, there are fun memes and markets and there's some money stuff and there are all these things, but outside of all that, the purpose of blockchains relates to the age-old elementary school unbreakable promise, the pinky swear. Let's get froggy. Nearly everything you do in life is the result of an agreement or a contract. Your chair was the result of an agreement to buy and sell lumber, to assemble and sell the chair to a retailer on Amazon. Then you made an agreement to buy the chair for $40. The lights in your house are powered by electricity, which is an agreement from you and the electric company. You agree to pay them. In return, they'll keep the lights on. The electricity that they generate is agreements between them and engineers who built turbines to generate the electricity. With insurance, you agree to pay some amount of money to them every month, and in return, they will do nothing. They'll cover your medical bills. Almost everything you do and everything you interact with is the result of some form of agreement or contract in some aspect. Now, agreements and contracts can feel kind of abstract and boring to really grasp onto. So to simplify, we can also refer to them as promises. When you get an oil change, they're promising that they will faithfully change your oil in exchange for money. When you put money in the bank, they promise to keep it safe in exchange for them to use your money to give out loans. When you buy a lottery ticket, the lottery promises to give you a fair chance at winning a ton of money in exchange for you buying the ticket. Whenever you make one of these agreements, in a way, you're asking them to pinky swear to not screw you over and to treat you fairly. But this doesn't always happen. Let's look at a real world example of someone breaking the pinky swear. Back in the 80s and 90s, McDonald's ran a promotion for people to win money by collecting McDonald's Monopoly game cards. The idea was simple. You buy McDonald's, and in return, you get a chance to win $1 million. You can imagine McDonald's literally going, "Hey everybody, I promise if you buy our McFood and McNuggets, we'll give you a fair chance of winning this money. Woo!"
But they ended up breaking this promise.
Instead of having a fair chance of winning, your chance was in fact zero. In the mid-90s, between $13 and $24 million went into the pockets of not people playing the game honestly, but a group of corrupt insiders who had rigged the game. Meaning that when you played the McDonald's Monopoly game, you were buying into a set of lies and promises that were 100% always going to be broken. And the thing is, it doesn't really matter if this was McDonald's fault or not. They were the ones making the promises that they ultimately could not keep. Another way you could think about it is that that's $24 million that they essentially stole from you and I. Now, if this system was deployed on a blockchain with something called a smart contract, it would have been impossible to defraud this $24 million due to smart contracts being immutable, decentralized, and transparent. But I'll get back to that in a minute. In all the agreements and contracts we make, imagine making a pinky swear with a 10-year-old and imagining how that agreement would hold up. "Hey buddy, could you please keep my money safe? You can play with it if you like, but just please have it when I come back." Immediately, you might get that worrying feeling in your chest that something might go wrong, that this 10-year-old might lose your money. You might be thinking, how could I trust them? Will they break their promise? And this feeling of, I can't breathe because of untrustworthy situations happens to us all the time. Can I trust this used car salesperson to give me a good car? Can I trust this tag that says machine washable, or will it make my shirt shrink? Will my insurance provider break their promise of covering my medical bills when I get hit by a bus?
When Patrick promises he'll go on a hike with me, will he actually?
Yes, Becca, I actually will. The issue with our current agreements and contracts is we have to trust the people who are making them to do the right thing. However, often, they're actually incentivized to not do the right thing. Insurance doesn't want to pay out money. Sometimes salespeople just want to get the shit off their shelves. And with my girlfriend, I promised to go on a hike, but I hate hikes. Where else has this happened? Now you might be thinking, okay, Patrick, this seems cool, but like, where has this actually affected me? Well, the McDonald's lottery that we just spoke about above. During the Great Depression, with the run of the banks promised to keep our money safe, and that when we went back to go get it, they would actually have the money there. And well and behold, there were times that they didn't have the money there. Just last year, Robinhood painted this amazing picture. Come use our application. We will give you access to the markets. We promise we will give you, a retail investor, a fair chance of interacting with the world of finance. Psych. But not this asset, this asset, this asset, or this asset. The 2008 financial crisis. Remember that? Shady deals behind closed doors combined with lies about financial product brought the world to its economic knees.
How are you f***ing us?
Hyperinflation in Zimbabwe. Hyperinflation in Brazil. Theranos. History is a relentless lesson of trustworthy entities being notorious promise breakers. And we finally have a way to fix it with smart contracts. Now, before I jump into smart contracts, a lot of people might be thinking, hey, cool and all. However, we have systems in place to protect against a lot of these things, which is true and which is great. And that is a very helpful step forward. But these systems often break. The ones in 2008 definitely didn't work. The ones with the Robinhood crisis definitely didn't work. And even if these systems apply and you go to court to try to work them out, maybe you're in court for years before you actually see a resolution. And by that time, what you needed the money for is long gone. So what is this technology? What is this tool that can fix this fundamental problem in our agreements today? This tool is smart contracts, and this tool is what the blockchain was built for. Now, I'm going to give you a quick overview of what a smart contract is. However, I'm leaving some links in the description for more in-depth explanations. But the basics of them is a smart contract is an agreement, a contract, or a set of instructions deployed on a decentralized blockchain. And once the contract or set of instructions is deployed, it cannot be altered, it automatically executes, and everyone can see the terms of the agreement. The real basics of it is that the code is executed by a decentralized collective, like a group of people, but a group of people running a certain software. This means that no one person or entity can actually alter any of these agreements or change the terms of the arrangement. In these traditional agreements, whoever owns the contract, whoever owns the execution of the contract can flip a switch and say, we're not going to do that anymore. In smart contracts, in Web3, in blockchain, you no longer can do that. Typically, these smart contracts are on a decentralized blockchain and used in combination with a decentralized Oracle network to get the real-world assets and information. And if these words sound like I'm conjuring up a magic spell, well, again, check the links in the description if you want to learn more about the technical implications. If you're not a technical person and you're not interested in getting to the nitty-gritty, you can kind of think of it like HTTPS. I bet the vast majority of you don't even know what HTTPS stands for, and yet you use it every single day whenever you log onto the internet. So how does this fix the McDonald's monopoly issue? In its traditional form, the lottery was executed behind closed doors. Somebody operated and owned the code and the contracts and the agreements that ran the lottery, and they had the power to alter it, and nobody other than the people internal on the lottery could audit this altering happening. Now, if the code for this lottery was deployed onto a blockchain, every time a hacker attempted to alter it, everyone would be notified. Not only that, but you couldn't even alter it because the terms of a smart contract cannot be altered once deployed. Combine that smart contract with a Chainlink VRF Oracle to get a verifiably random number, and presto, you now have a perfectly decentralized, unalterable agreement that is impossible to hack, commit fraud, or manipulate. We have just saved the public between $13 million and $24 million just by fixing the issue of trust. How does this fix Robinhood? Well, the problem with Robinhood is already fixed, right? Again, the problem is that there's a centralized body that can flip a switch at any time and say, yeah, you can't access these markets anymore. We're breaking our promise of actually giving you access to the markets. This is already fixed with something called decentralized exchanges, and these exist today. One of these exchanges is one called Uniswap. You can swap ERC20 tokens, which are kind of the equivalent of stocks, but some aren't, some are. It's a little confusing. I won't get into that here either. But it doesn't have that centralized body that can flip a switch and ruin access to the markets. And had these investors been on a decentralized exchange, it would have saved them hundreds of millions of dollars. And it would have prevented fraudulent market manipulation. How does it fix run of the banks? With transparency built in and automated solvency checks, you can build a bank-like smart contract that has insolvency checks built in that make it impossible to get there. Insolvent means broke as f. Any agreement or any history lesson where there was a trust assumption that was broken, smart contracts can be applied to and should be applied to, especially in a time where big money runs, owns, and controls everything. We desperately need to move to a world where some self-interested centralized entity can't flip a switch and ruin people's access to the services that they need. We can move away from a world that is brand-based to a world that is math-based. Right now, if you interact with a service that you don't like or that they break their promise, the only thing you can do is walk down the street to the next service that's going to make the same set of promises, and you have to hope and pray that they're actually going to keep it. We can move from that to a world where we can just look at the math and say, oh, okay, 1 + 1 = 2. This is what this agreement is going to do for me every single time, guaranteed. Because it's a decentralized autonomous agent, has no incentive to be evil, and everything is transparent and out in the open. If I'm a big company, and if it was better for me for 1 + 1 to = 3, maybe I would go behind some closed doors and fudge some numbers and come back out and be like, hey, 1 + 1 = 3. But with smart contracts, that's impossible. Doing the right thing is infrastructural. Now, given the choice between two agreements, one where you have to trust a single centralized entity that they're going to do the right thing for you, versus a decentralized, untamperable collective, which one are you going to choose? I'm picking the one that can't screw me over every single time for every agreement I can apply it to. Now, this technology is relatively new, but we have already seen it re-landscape entire markets and continue to do so. The traditional financial world is already getting its lunch eaten by DeFi, or decentralized finance. There's already over $200 billion of people's money in these protocols to help have a more fair, more accountable, more transparent financial system. This DeFi movement is one of the main reasons I got into this space, because we desperately need to move away from where we are right now and end people's chances for wealth being sucked up by some group that's bending the rules in their favor. And smart contracts are our ticket to that better world. More and more industries are also coming over to smart contracts and blockchain because of all the innovations and because of all the advantages that it has. As we grow and as we get better, we get closer to this vision of having this concept fulfilled. Trust minimized agreements. These smart contracts are minimizing the trust that we need to give other people in order for these agreements to be executed. If trust minimized agreements is too confusing for you, just say unbreakable promises. Now, I gotta be honest with you guys. Blockchains and smart contracts and cryptocurrencies can actually do more than just trust minimized agreements. What? They have security benefits, uptime benefits, execution speed benefits, and a whole lot more. But it's a lot easier to just learn about one and learn the other ones later, right? It's kind of like sprinkles on top. So this is why we are here. This is why we're building this future. And this is why we are so excited about it.
Last year, 2022, there were a lot of issues with a couple different companies, like, for example, SBF's FTX platform. The thing to me that's most frustrating about that situation is that FTX platform wasn't anything that I just talked about. It wasn't decentralized. It wasn't trustless. It wasn't transparent. It was purely a traditional Web 2 company pretending to be Web 3 and just using the cryptocurrency part of Web 3, but not actually using the smart contracts. And we're doing a much better job as a community getting rid of the bad actors. And this is something that's incredibly important for you when working with protocols and when building protocols. I want you to be incredibly successful here, but I want you to be incredibly successful because you're making a ton of value. A lot of these platforms that we saw collapsing last year were not creating value. They were stealing value. They were siphoning value. They were faking having value. And as you learn and as you build smart contracts yourself, it'll start to become innately aware of what protocols and what companies are centralized and are not the ethos of Web3 and the ones that are. We are building verifiable, trust minimized agreements, unbreakable promises. And if you can't verify those promises, then it's not trust minimized. It's not Web3. It's not what this industry is for. That's what I want you to do as you finish this course, is be a force for good. Unfortunately, because a lot of people haven't taken my course, not everybody understands the difference between a legitimate project and a token that's just meant to pump somebody's bags. As this space continues to grow and as people like yourself take courses like this, we will get to continue to push real legitimate projects forward and wash out the projects that aren't actually contributing to Web3.
Whew. Even in just this introduction part, we've learned a ton. So let's do a quick summary of what we've learned so far. Bitcoin was the first protocol to take this blockchain technology into the limelight and take these cryptocurrencies into the mainstream. Bitcoin is a sort of digital gold, or a store of value, able to make transactions between users in a decentralized manner. Ethereum and other smart contract platforms take this blockchain technology one step further, enabling people to make smart contracts and decentralized trust minimized agreements. These smart contracts and decentralized applications can access and interact with the real world using something called decentralized Oracle networks. Chainlink is a decentralized network that allows us to build these hybrid smart contracts, which combines our on-chain logic with our off-chain decentralized data and decentralized computation, giving rise to our logic being completely decentralized and our data and external computation being completely decentralized,
giving us all the features that traditional agreements and traditional contracts have. Now, these digital currencies like Ethereum and Bitcoin have value even without the smart contract part. Having a censorship-resistant, decentralized store of value is immeasurably powerful in its own right. We have some links in the GitHub repository that'll teach you how this decentralized store of value flips traditional finance on its head. And it's another one of the great reasons for building smart contracts. But again, the easiest way to boil it down is trust minimized agreements or unbreakable promises. But let's also go into some of these other features that smart contracts have over our traditional environment. The first feature, of course, is that they are decentralized and they have no centralized intermediary. The different individuals that run one of these blockchains are known as node operators. And it's the combination of all these thousands of node operators running the same software, running these algorithms, running these smart contracts that make the network decentralized. We'll dive deeper into how that works later. The next feature is transparency and flexibility. In these decentralized networks, since all these individual node operators run this software, everybody can see everything that's happening on chain, meaning there's no shady deals, there's no weird things happening. Anything that's going to be unfair, people would be able to see and just not use. Everybody has perfect information and has to play by the same rules. Now, additionally, this doesn't mean that there's no privacy. The blockchain is pseudo-anonymous, meaning that you aren't necessarily tied to an identity in real life. They also have the feature of speed and efficiency. For those of you who have ever tried to do a bank transfer or send money across seas, you know it sometimes can take 2 to 3 weeks, when in fact, all these banks are really doing is basic math. They're subtracting money from your balance and adding it to some other balance. Why does it take so long? In the blockchain, all of these transactions happen instantly. Another instance for those in the financial world today know that clearinghouses and settlement days can take a long time. In the blockchain, there's no need for any of that because they happen instantly. This obviously is much quicker, but it also makes for much more efficient interactions with each other. Security and immutability. Again, immutable means that it can't be changed. Once a smart contract is deployed, that's it. Whatever's in the code is going to be in the code forever. They cannot be altered or tampered with in any way. This means that the security is much easier. Whereas in a centralized world, somebody can hack into the server, jump into the database, and change some numbers. You can't do that in the blockchain world. And since it's decentralized, in order to hack the blockchain, you'd have to take over half of the nodes, as opposed to in the centralized world, where you only have to take over one. In the regular world, if your computer and your backup computer go down, all of your data is gone. In the blockchain world, if your computer and your backup computer go down, all your data is safe because it's being run on all these other decentralized nodes. And even if a few hundred nodes or if a few thousand nodes go down, it doesn't matter because as long as one node has a copy of the blockchain, you're good to go. Hacking a blockchain is nearly impossible and leaps and bounds more difficult than hacking a centralized server. Not only that, but this is safer in the asset sense as well. All you need to access your credentials and your information and your assets is your private key, which is basically your password for all of this. And as we've discussed in the video, these smart contracts remove this counterparty risk, remove this centralized intermediary, remove these trust gateways that we have to do in Web 2. When we engage with users and individuals, they don't always have our best interests at heart. Smart contracts remove this counterparty risk because once one of these contracts is created, they can't go in and they can't alter it, and they can't let greed or ego or anything else get the better of them and alter the terms of the deal. And as we said, this gives rise to these trust minimized agreements or these programmatic unbreakable promises. We move away from brand-based agreements to math-based agreements, where we can look at the cryptography, we can look right at the code and see exactly what something is going to do and how it's going to execute, versus having to rely on a human being doing the right thing. With smart contracts and decentralized hybrid smart contracts, doing the right thing is infrastructural. All these pieces boil down to us having the freedom to interact the way we want to interact without having to be afraid that interacting like that is going to screw us over. This trust minimized piece, these unbreakable promises, make interactions so much better. In the purely Web 2 world, we're constantly bombarded with messages of projects and protocols pushing us to move or act in the direction that makes them more profitable. Versus in the smart contract space, we can see everything transparently and we can even engage and interact and be partially owners of the protocols and the interactions that we decide that we want to be a part of. So smart contracts have been around for a few years now, and what have they generated for? What industries have come about due to these smart contract platforms being around? Well, you've probably heard of some of these, and some of these we've already mentioned, but let's give you a quick refresher. DeFi. DeFi stands for decentralized finance, and it gives users the ability to engage with finance and markets without having to go through a centralized intermediary. For example, like we said with Robinhood, you no longer have to trust that Robinhood would continue to give you access to the markets. You instead would be able to see in the smart contract, yes, I have access to the markets. Or in the 2008 financial crisis, you never have to trust that these groups and institutions are giving you the correct things on the back end. You can see everything transparently right on the blockchain. You can engage with things like money markets and sophisticated financial products easy, effectively, and securely. If you're really excited about DeFi, we have a ton of DeFi examples showing you how to build and interact with these protocols in coming lessons. DAOs, or decentralized autonomous organizations, are another group that we've already mentioned. DAOs are groups that are governed completely decentralized by a set of instructions or smart contracts on chain. There are some massive benefits here where engagement's much easier, the rules are black and white, and you can see everything directly on chain. Voting and governance technology is completely decentralized. And the blockchain space is one of the big ones pushing how we can evolve politics and how we can evolve governance to make it more efficient, fair, and reasonable. And you better know it, we have some examples of how to build DAOs and how to work with DAOs in coming lessons. So be sure to watch those. NFTs stand for non-fungible tokens and can really be kind of described as digital art or just a unique asset. They can do so much more, but we'll keep it high level for now. Projects like Bored Apes and CryptoPunks have revolutionized the way that people get paid for their work, show off their creativity, status, and so much more. And yes, of course, we have lessons showing you how to create and interact with NFTs as well. So many other groups and so many other industries are being created as a result of this insane technology. And maybe after finishing the journey with us here, you go out and you'll be the one to pioneer the next industry or the next billion-dollar idea. You've learned so much already. But now that we've learned a lot of this high-level information, let's finally jump in and let's make your first transaction and let's get you set up to interact with this new world. In this next section, we're going to get you a wallet and we're going to show you exactly what a transaction looks like and feels like. Let's dive in.
This is the Ethereum website, ethereum.org. We are going to make a transaction on a test Ethereum blockchain. I'll explain what that means in a little bit. This is going to be our first ever transaction that's made on the blockchain. And this process of making a transaction is going to work the exact same across all EVM compatible blockchains and layer 2s, like Arbitrum, Ethereum, ZK Sync, and etc. I'll explain what EVM means in the future. For now, just follow along and have fun running your first transaction. Now, in order for us to send a transaction on any of these EVM chains, the first thing that we need to do is set up a wallet. So I'm going to go to MetaMask because it's one of the most popular wallets and one of the easiest wallets to use. I'm using the Brave browser, but it works for Chrome or Firefox or really any other popular browsers out there. And it's just going to be an extension in the top right hand of our browser. It's going to make it very easy to see anything to do with our wallets and our transactions very easily. And it's going to store all of our EVM-based currencies and EVM-based transactions. So I'm going to go ahead and hit Add to Brave, Add Extension, although Brave does also come jam-packed with its own wallet. So now we come to the Get Started page, and I'm going to go ahead and select Create a New Wallet. Sure, we'll agree to help out MetaMask. Now we're going to create our password, make sure it's really secure. For the purpose of this demo, mine's going to be kind of mediocre. Now I'm going to preface this. This wallet that you're making right now, as you follow along with me, this is going to be your development wallet. So if you want to make the password a little bit weak, just so that you can test things out very quickly, go for it. Just know we're never, ever going to put real money into this wallet. It's good if you treat this as if it is a real wallet. That way you'll get used to and you'll get familiar with good wallet safety. You'll then get a video like this, which will teach you about the secret recovery phrase, which we saw a little bit earlier when we were creating our wallet. Let's watch this video.
MetaMask is a new way to connect to sites and applications. On traditional websites, a central database or bank is responsible for controlling and recovering your accounts. But on MetaMask, all of the power belongs to the holder of a master key. Whoever holds the key controls the accounts. Your secret recovery phrase is your master key. It's a series of 12 words that are generated when you first set up MetaMask, which allow you to recover your wallet and funds if you ever lose access. It's important that you secure your wallet by keeping your secret recovery phrase very safe and very secret. If anyone gets access to it, they will have the master key to your wallet and can freely access and take all of your funds. To secure your MetaMask wallet, you'll want to safely save your secret recovery phrase. You can write it down, hide it somewhere, put it in a safe deposit box, or use a secure password manager. Some users even engrave their phrase onto a metal plate. Nobody, not even the team at MetaMask, can help you recover your wallet if you lose your secret recovery phrase. If you haven't written down your secret recovery phrase and stored it somewhere safe, do it now. We'll wait. And remember, never share your secret recovery phrase with anyone, not even us. If anyone ever asks you for it, they're trying to scam you. That's it. Now you know what a secret recovery phrase is and how to keep your wallet safe and secure.
Awesome. So that was a great introduction to keeping your wallet safe. We'll talk a little bit more about safety with our wallets in the future. Let's go ahead and select Secure My Wallet. Now, this is where we need to write down our secret recovery phrase and save it in a very secure place. It gives us some tips here, like a password manager, a safety deposit box, or split it up and keep it in multiple secret places. For the purposes of this video, I'm going to be showing you the secret recovery phrase because I'm not going to put any real money into this, but you should never ever do this. Additionally, you'll sometimes hear mnemonic as a synonym for secret recovery phrase. The main takeaway from all this is you should never share any of this. This is for you only. If you show this secret phrase to anybody else, they will have access to not just one account, but every account that you make in MetaMask. So be absolutely certain to not share this with anybody. So again, I know I'm belaboring the point a little bit, but everything that we're going to do in this tutorial, we're going to do with fake money and fake assets, and never put actual money into this account that we're making here. Once you get familiar with using MetaMask and working with the tools and staying secure, then you can go ahead and create a separate MetaMask that will have real funds in it. If you want to put real money in different MetaMask, a lot of browsers have a profile option, and maybe you can make a new profile, install MetaMask on that different profile, call that profile Real Money Profile or something, and that's where you will store your money. But for this video, for this tutorial, the MetaMask that you are using is going to be specifically for testing things out, and you will never store real money to it. I'm going to harp on that a lot more in this course. So even if you're coming here and you have a wallet, I highly recommend still making a brand new one for this tutorial, just in case you don't accidentally code something or do something autonomous and give away your funds. If this is your first wallet, then great. But again, when you're working with real money, if you lose access to the secret phrase, you will lose access to all your money. So be sure to write this down. Promise me that you won't use real money for this course. Great. I'm going to hit copy to clipboard for now, and we're going to go ahead and hit next. Now we need to confirm by adding our seed phrase back in. We can go ahead and hit confirm, and we now have created our wallet. Let's go ahead and select got it. Awesome. Now we can see the interface of our MetaMask full screen. And depending on your browser, what you can normally do is hit this little puzzle piece on your browser and select this pin button. So now we can pin our MetaMask into the top of our browser. And we can click it like so, and we can see it give a little drop down like this, and we can see the same information in this little drop down as there is on the full screen. Now, even if you lose access to that page, now that this is bookmarked in your browser, you can select your MetaMask, select these three dots, and hit Expand View to reach this tab. Now, additionally, what we can do in here is we can actually go up to our accounts, and we can actually create multiple accounts by hitting Create Account. And if you wanted to, you could give it a name here. I'm just going to leave it as default for account 2. And now we have 2 separate accounts. We have an account 0 with an address, and an account 2 with an address as well. Both of these accounts actually share that same secret phrase. So anybody with access to the secret phrase can actually have access to both accounts. However, they have different private keys, and that's what makes them different. We'll talk a little bit more about that in the future. If somebody gets access to a private key, they'll get access to a single account. If they get access to the secret phrase, they'll get access to all the accounts that you make. Even, if you made a third one, they'd get access to this one as well. Now, if you look up in the top right of the screen here, you'll see this section that says Ethereum Mainnet. This is our networks tab. And if you click it, you can see all the different networks that our MetaMask has access to. Ethereum mainnet is the main network of Ethereum, and this is where real money is spent and used. For this course, we're not going to be working with Ethereum mainnet. We're instead going to be working with something called a testnet. For both engineers and non-engineers, we often need a place to test or simulate our transactions. And for the developers here, throughout this course, we are going to teach you another technique for testing out your transactions on a local network. And a local network is actually going to be the preferred way we do our testing and our simulations. However, it's still really important to see end-to-end what a real transaction looks like, and that's what a testnet will do for us. It simulates exactly what a mainnet or a live money network would look like. However, there's no real money at stake, and we don't actually have to spend any money. To see some of the testnets that come default with MetaMask, we can hit the show/hide button, which will bring us to the settings page of MetaMask. We can turn on show test networks. And if we scroll back up, now if we hit our networks tab, actually, let's go ahead, close out of settings. Now, if we hit this dropdown, we can see Gorilla Test Network, Sepolia Test Network, and Linea Gorilla Test Network. These networks are test networks that resemble Ethereum or Polygon or Linea or Arbitrum or Optimism or ZK Sync or any other EVM compatible chain that we want to work with. And again, we'll define EVM in the future. And we can actually switch the network that we're working on simply by clicking another network. So let's switch to Sepolia. We can see our network changed up here, and now we can see we have 0 Sepolia ETH. So on ETH mainnet, this new account has 0 Ethereum, and on the Sepolia test network, we also have 0 Sepolia ETH, which makes sense because this is a brand new wallet. And we haven't put any money into this brand new account yet, so of course we have 0. At the time of recording, Sepolia is one of the most popular test networks out there. So we're going to be working mainly with Sepolia throughout this course. However, testnets often change because, again, they're run out of the goodness of people's hearts, and sometimes people stop running them. You should absolutely have either the web3dev.education site up or the GitHub repository associated with this course. And an important note, sometimes you'll see this as the ChainExcel.org Foundry Full course. We recently renamed it to the Cyphren Foundry Full course. So this is the correct link, but if you see ChainExcel.org, that's fine as well. And you should scroll down to the recommended testnets section to make sure you're on the most up-to-date testnet. At the time of recording, like I said, we're working with Sepolia. Throughout this course, we are going to show you how to work with different testnets and different networks as well, because it's incredibly important to do so. The blockchain world is moving into a multi-chain world, and especially with the popularity of L2s, which help Ethereum scale, learning the differences between different chains and different L2s is incredibly important. Now, same as Ethereum, what we can do is we can actually go to Sepolia Etherscan. So we'll go to sepolia.etherscan.io, and we can grab our address from MetaMask by clicking and copying the address here, pasting it into the Sepolia Explorer, and same as Ethereum, we can see our account balance, we have 0 ETH, there are no transactions, no token transfers, nothing, because obviously it's a brand new wallet. Now I'm showing you this because pretty soon we're going to send our first ever blockchain transaction. If you've never sent a blockchain transaction before, we're going to do it on this testnet to give you some confidence as what a transaction actually looks like when you do move over to a mainnet. And I'm showing you this site now because you're going to see when we send a transaction, a lot of this information is going to get updated. Now, just remember, like I said earlier, a testnet is run out of the goodness of people's hearts, so please use the transactions sparingly. Once you send your first transaction here, try not to send too many more, as one is good enough for you to see what's going on anyways. And in order for us to simulate one of these transactions, we're going to go to a faucet for a testnet. Testnets have this thing called faucets, which allow us to get some free Sepolia ETH so that we can test out sending transactions and receiving transactions. If you go to the GitHub associated with this course or web3dev.education, we can scroll down to this testnet faucets section and select one of the links to go to one of these testnet faucets. Right now, the recommended faucet that we're working with is faucets.chain.link, but be sure to use the GitHub repo or web3dev.education to be most up to date. What this is going to do is we're going to ask this faucet site to send us testnet Ethereum. And this is why this testnet Ethereum isn't worth any real money, since we can get it for free anytime that we want. These obviously don't exist on mainnet. You can't get free mainnet Ethereum via a faucet. Now, what we can do is we can actually connect our wallet to this site and we can get some free testnet Sepolia ETH. This will make it so that in our balance here, we'll actually have some Sepolia ETH to play with. So to do this, what we're going to do is we're going to go ahead and hit connect wallet, accept the Chainlink terms of service. I've already read them. Our MetaMask is going to pop up to connect it to this website. Now get familiar with this interface because this is how websites will interact with our wallet and interact with the blockchain. Connecting our account to the site, we'll first select the specific account that we want to connect. We're just going to choose account 1. We'll hit next, and then we'll go ahead and hit connect. And now we can see our wallet address in the top right, and we can see that we're connected on the Ethereum Sepolia testnet. If we go up to our wallet and we actually switch to Ethereum mainnet, you can see that the website has actually changed this little dropdown to Ethereum mainnet. And if we go in here, we can actually switch to Ethereum Sepolia, and our MetaMask will pop up with this switch network button, which will help us switch the network for us. So now we're back on Sepolia test network. Connecting to these websites is how we give these websites a way to interact and connect with our wallets. We can go ahead and select this, hit these 3 dots, and hit disconnect this account. But don't worry, anytime we want to send a transaction, the website has to ask us if we want to send a transaction. So just by connecting to the site, it won't actually send a bunch of transactions for us. And if we scroll down, we can see our wallet address is placed right here. And we can see we can request test link, and we can also request test ETH. For now, we don't need any test link, so we're going to leave that off. But in the future, we will come back to the site to get some test link. For now, we're just going to get 0.1 test Ethereum. And if all goes well, we should hopefully see it in our Sepolia ETH here. In order for us to get this test Ethereum, we do have to log in via Twitter. If you don't have a Twitter, you can use any of the other faucets in the testnets faucets area of the GitHub, such as the Alchemy Sepolia faucet or the Sepolia proof of work faucet. But if you are on Twitter, now's a great time to give me a follow, maybe give me a shout out, and maybe say, hey, sending my first transaction. Thanks, Patrick Alpha C. Boop. Or not, whatever you want to do. Just some light shilling of my own Twitter account. Anyways, we can log on via Twitter. We can authorize this app, verify that we're human, give our AI overlords the prompt here. Oh, make sure we don't select the link, and let's go ahead and send the request. Now, what's going to happen is it's going to give us this transaction hash on Sepolia. And after a delay, we'll see it go from initiating to waiting for confirmation to token transferred, and we'll see a transaction hash. And if we click the transaction hash, we'll see a transaction that was sent to our address. So this will be the first transaction that we get to see. And there's a ton of information here. But the most important piece is if we open up our MetaMask now, we can see we now have 0.1 Sepolia ETH in our account. And if we copy the address again, we paste it into here, we can see now we have a 0.1 ETH balance. You might have to wait several minutes for the transaction to finish going through. And if you accidentally refresh your browser, again, we can go ahead and just select our MetaMask, copy our address, and paste it into Etherscan, or just view it right in our MetaMask here. And if you missed that piece about the transaction data, if we go back to Etherscan with our address, remember we're on Sepolia Etherscan, and we scroll down, we can see this most recent transaction hash that just occurred. And we can click the link here and we can see that detail about the transaction again here. Now, importantly, remember though, this is on Sepolia. If we switch back to mainnet Ethereum, you'll see we have 0 ETH on mainnet Ethereum. If we switch to Gorilla test network, you'll see we have 0 Gorilla ETH on that network. If we switch to Linea Gorilla ETH or any other network other than Sepolia, you'll see that Sepolia is the only one that has the 0.1 Sepolia ETH. If you want to practice working with a different testnet, feel free to scroll up back to the faucet, select a different testnet, and try to get testnet in one of these different testnets. Just be sure to take a look at what testnets your MetaMask comes with, since some of the networks this faucet is compatible with don't come built into our MetaMask. But again, like I said, in the future, I'll teach you how to add these different networks to our MetaMask in the future. But huge congratulations, you received your first transaction. Because again, this faucet is us asking them to send us money. It's not us sending money, it's them sending money to us. And if this is the first transaction that you've ever sent, you should be proud of yourself already. Give yourself a big pat on the back. And here's a picture of me holding a cat with that cat's face all over my pajamas as a congratulations. Now, once more, let's grab our address, paste it into Etherscan here, and scroll down. And we're going to learn a little bit more about what actually went down, what actually happened in this transaction. You can see on Etherscan, it gives us some basic details. It says from and to. From is going to be another address, a different address, an address controlled by the faucet, and to is obviously going to be our address. And if we select this transaction hash, we can see even more details in here. Understanding all these different fields is essential to becoming a smart contract developer and even just a Web3 or Ethereum or blockchain user. So let's learn a bit of the basics of what's actually going down in this transaction. The first field on this page is the transaction hash. You can even see a little question mark here, which tells you a little bit more about it. It's a unique identifier for this specific transaction on this network. So this specific transaction hash, we can even copy and paste this into the address bar, and we'll get the exact same transaction back. This is the only transaction in the entire blockchain that will have this transaction hash. It's the unique identifier. It identifies the transaction of sending 0.1 ETH from the faucet address to our address. We can see the status of this was successful. We can see the block number and the number of block confirmations, which we will explain in the future. We can see the timestamp, which of course is when this transaction occurred. We can see the from and to, who initialized the transaction and who it was sent to. If we select this from and open this in a new tab, we can see some details about who actually sent us this test ETH. And if we go back to the transaction detail and keep going, we can see the value here, which again, if we roll over, it's the value of Ether or testnet Ether. And then in parentheses, the fiat value or the dollar value, which of course, since this is a testnet, it's always going to be 0. The value of this transaction was 0.1 ETH. Now, what's underneath this value thing, this transaction fee and this gas price thing? What are these? If we zoom in a lot more to these pieces here, and we roll over transaction fee, we can see it says it's the amount paid to the block producer for processing the transaction. And then gas price is going to be the cost per unit of gas specified for the transaction in Ether or Gwei. The higher the gas price, the higher the chance of getting included in a block. I'm going to explain that in a little bit, but if we scroll down even more, let's zoom back out, and we click to show more, we can see even more details about this transaction. For now, we're just going to click to show less and just focus on the details that are here. So let's talk about just the concept of transaction fees and gas for a second, because they are important concepts for you to understand. Remember how I said that these blockchains are actually run by a group of different nodes? Well, the question is, what's their economic incentive to keep running these blockchains? Are they running them out of the goodness of their heart? Well, on a real network, these nodes actually get paid a little bit of Ether for processing transactions. Whenever you send a transaction, there is a node, sometimes referred to as a miner or a validator, depending on the network you're on, who gets paid a little bit of the native currency of the blockchain to process that transaction. For Ethereum, they obviously get paid in Ethereum. Or for test Ethereum, they get paid in test Ethereum, which again, the test Ethereum is worth nothing, which is why I said they're running them out of the goodness of their heart. If you're sending a transaction on the Polygon network, they're going to get paid in Matic, the native token of Polygon. If you send a transaction on an L2 like Arbitrum or Optimism, you're going to get paid in ETH, which is the native token of those L2s. This payment is obviously to incentivize people to continue to run nodes. And they get paid more the more gas you use. So what is gas? Gas is a unit of computational measurement. The more complex your transaction is, the more gas you have to pay. For example, if we hit more details just really quickly, and I zoom in a little bit more, we can see this section here, gas limit and usage by transaction. This means that when we sent this transaction, we limited it to a maximum of 60,000 gas, but in total, we only used 21,000 gas. This 21,000 gas represents how complex this transaction was. It was 21,000 gas units worth of complexity. Now, for simple things like sending Ether, the units of gas are usually pretty small. For example, 21,000 units of gas is actually a really small amount of gas being sent. But maybe for more complex transactions like minting an NFT, depositing some funds into a DeFi protocol, or deploying a smart contract, those are typically going to be more expensive transactions because they're more complicated. They have to do more stuff. In the future, we'll introduce you to this concept of EVM codes or opcodes. And If you break down a transaction to the lowest level, this assembly opcode stuff, you can actually see exactly how much each opcode costs in terms of gas. Don't worry about this at all right now. Just know that these transactions are broken down into many, very, very small instructions, and each instruction has a specific amount of gas. The more instructions usually means more gas. Like I said, we'll explain this much later in the course. Don't worry about this too much here, but just know that we use 21,000 gas. Now, if you take this gas used and multiply it by the gas price in ETH instead of GWE, so we'll take 21,000 and multiply it by this gas price in ETH, not in GWE, and hit enter, we'll see the total transaction fee of the transaction. And you can see that this number does indeed match the transaction fee. For you to understand how much ETH you're going to pay for your transaction, you multiply the gas price times the gas used. Transaction fee equals gas price times gas used. So this means that whoever sent us this 0.1 ETH also paid 0.0000525 blah, blah, blah ETH to a blockchain node, to a validator on the Sepolia Ethereum testnet. Now, each blockchain has their own unique way of calculating how much transaction fee someone's actually going to pay. For most EVM chains, this is the simple algorithm. It's going to be gas used times gas price. After we understand how the blockchain works more in depth, I'll explain to you what the rest of these values stand for. For now, just know that anytime you make a transaction on chain, you have to pay the validators or the blockchain nodes a little bit of gas or a little bit of the native token of the blockchain, which in our case is ETH. So you have to pay a little bit of ETH to the blockchain nodes providing or sending the transaction. Sometimes I'll refer to this just as transaction gas. Let's look at an example of this ourselves. If we pull up our MetaMask, we go ahead and hit expand view. As we know, we have two different accounts in here. We have account 1 and account 2. Account 1 has 0.1 Sepolia ETH. Account 2 has 0 Sepolia ETH. If I send 0.05 from account 1 to account 2, how much do you think I'll have left in account 1? Let's go ahead and do this. And this is going to be the first transaction that you send on the blockchain, which is incredibly exciting as well. Let's go ahead and hit this send button in our MetaMask. We'll hit send. We'll hit transfer between my accounts. We'll select account 2 and we'll say 0.05 Sepolia ETH. So we started with 0.1 Sepolia ETH and we're going to send 0.05 to account 2. We'll scroll down. We'll hit next. We can see some information here about what's actually going on. We can see some gas information, which MetaMask automatically prompted for us. And it even gives us the total amount that we're going to be paying in ETH. It's adding this 0.05 ETH to the estimated amount of gas that we actually have to spend. So that at the bottom, it says the amount plus the gas fee is the two of those combined, the value that we're sending plus the gas fee. And additionally, in MetaMask, if you select this here, you can get some more information about editing our gas fees. The amount of gas that you choose to spend can be different depending on how many people are making transactions on the blockchain. The more people are sending transactions at the same time, the more expensive gas costs are going to be. So if a lot of other people are also sending transactions right now, the gas price is going to be higher. If a lot of people are sending transactions, that means there's not going to be enough space for everyone's transaction to get through. So in order to throttle that, they increase the gas price. That's a bit of an oversimplification of what's happening, but if you take that understanding, that'll pretty much work. If you want to specify exactly how much gas you want to spend, you can click the Advanced tab. If you select 0 gas, there's a high likelihood that your transaction will never go through. So we're just going to go with the default, which is usually a good idea. So let's go ahead and confirm. We now see a send transaction in our queue in the activity tab of our MetaMask, which shows us that we have a transaction currently sending. And if we click on it and click View on Block Explorer, it'll actually open us up on Etherscan, and we'll see, well, mine was a little bit quick, but normally we'll see a little indexing tab, and we won't see this having gone through. We'll see it as like indexing or sending or something like that. But after a little bit, it'll actually finish sending. You might have to wait a minute or so for this to actually finish going through, but it looks like mine was really quick. And same as our last transaction, this has a lot of the same information. And if we scroll down, we'll see that, of course, we sent a different amount of ETH, 0.05, and we have a different transaction fee. Now, if we pull up our MetaMask, what do you think that we're going to see? We're going to go ahead and click Expand View again. And we see account 1 says 0.05, and account 2 also says 0.05. That's kind of odd. I thought we spent some gas. Well, if we click on the big accounts button, we can see exactly how much ETH is in each account. We can see we have 0.0499 in account 1 and 0.05 in account 2. And we can see in our activity history, our account 1 recently sent 0.05 ETH, and account 2 recently received 0.05 Sepolia ETH. Now, here's the best part of all this. Even if you don't want to become a developer, you just learned the basics of sending a transaction and interacting with sites using your MetaMask. Congratulations.
Now, here's something that's incredibly exciting. With just this little bit of information, you now know how to interact with blockchains and interact with the Ethereum protocol. So if you don't want to learn how to code anything, you can go and you can start interacting with Ethereum and interacting with protocols with just this much information. However, I know most of you guys are here to learn how to code. So let's look under the hood of Ethereum and what is actually going on with these transactions and with these gas and with these blockchains and what's really going on. Let's learn all the fundamentals of a blockchain. Now, if you want to just go ahead and jump into the coding, go ahead and grab a timestamp from the description. However, learning exactly how the blockchain works is going to make you an incredibly powerful developer. So let's take a look at that first. So we're going to be going through this blockchain demo on this site right here. Now, the creator of the site has a fantastic video and a fantastic walkthrough, Blockchain 101. It is right on their site. So if you're looking for another explanation, definitely check out his video. It is absolutely fantastic. But the first thing that we really need to do in order to understand blockchain, in order to understand really anything and everything that's going on here, we first really need to understand this SHA-256 hash or hashing just kind of in general. Let's first understand what a hash is. A hash is a unique fixed length string meant to identify any piece of data. They are created by putting some piece of data into a hash function. In this example, the hashing algorithm used is SHA-256. Now, Ethereum actually uses this right here for its hashing algorithm, which isn't quite SHA-256, but is in kind of this SHA family. But it's really just another way to hash things, and the specific hash algorithm doesn't matter so much. So this example uses SHA-256, but you can imagine it's the same as the Ethereum hash. They're just going to result in a different hash. So what's going to happen in this application here is whatever data or whatever information we put into this data section here, as you can see below, this hash changes. So what's happening is this data is running through the SHA-256 hash algorithm, and it's outputting this unique hash. So this hash is a unique fixed length string that's going to identify like a blank data piece here, right? So if I put in, my name, like, Patrick Collins, this is the hash that's going to represent Patrick Collins, right? And you can see, even when I put, tons and tons of data in here, the length of the string doesn't change, right? So it's always going to be the same amount. We can put almost any amount of data in here. There is an upper limit on the max size of the data, but for all intents and purposes, we can pretty much put any length in here. And you'll see too that, every time I type in Patrick Collins, this hash is always going to be this 7E5B, right? I'm going to delete it. I'm going to do Patrick Collins again, 7E5B. It's always this unique hash is always going to be unique, right? It's always going to be this fixed length string here. So now we can take this idea, right, of putting this data in here, and we can move on to this concept of a block. So with this block concept, we're going to take the exact same thing with this hash, this data section, right? But instead of having everything just being in this singular data area right here, we're going to split this data up into block, nonce, and data. So what we're going to do is we're actually going to hash all three of these to get this hash, right? We're going to put all three of these. We're going to say all three of these are combined together. We're going to put all three of them into this hashing algorithm to figure it out. So if I type a bunch of stuff here, we can see that block 1 with nonce, this nonce and this data, we're going to get this hash. And as you can see, actually, the screen turns red. This block turned red. Now, what happens when I hit this mine button? When I hit this mine button, it's actually going to take some time. It's going to think for a little bit. And we can see that the nonce here actually changed, right? The nonce is different from what it was before. And this hash now starts with 4 zeros. Okay, and then the back turned green.
when we're talking about mining, we're talking about miners solving some type of very difficult problem that takes a lot of time to do. Now, in this example here, the problem that the miners had to solve was they had to find a nonce or a value in this nonce section that when hashed with at block number 1 with this data, it would start with 4 zeros. So the problem here the miners had to solve was to start with 4 zeros. And the only way for them to really do that is kind of this brute force, trying stuff. So they tried 1, okay, 1 didn't work. Okay, 2, nope, 2 didn't work. 3, no, 4, 5, 6, okay, 5, well, that started with 1 0, but that's not 4. And they have to keep trying all these numbers until they get to this one where, let's hit mine again, where it has 4 zeros at the top, at the start. Now, this specific problem changes blockchain to blockchain, right? Ethereum has a different problem for miners to solve. Bitcoin has different problems for miners to solve, but this concept is going to be the same.
And since Ethereum is proof of stake now, nodes actually take turns solving these problems. Again, we're not going to go too deep into that right now, though.
So they have to take one block is going to be this concept is going to be all this data. It's going to be the block number, and it's going to be this nonce, right? And so this nonce is the solution, is going to be the number that they use to get like the solution to the problem, right? So if I go to 1 here, and I do this again, we're going to hit mine, and the nonce has changed, right? It went from 1 to 33,128 because this is the nonce that allowed this hash to start with 4 zeros. And so that's what's happening when blockchain miners are mining. They're going through this process, this very computationally intensive process of trying to find a nonce that fulfills whatever the problem is. So that's really it, actually. So that's a block. And that's really what's happening when miners are mining. They're just looking, there's trial and error, brute force, trying to find this nonce. So now that we know what a block is, let's go to the next step and figure out, okay, well, what's a blockchain? So here we have an example of what a blockchain is going to look like, right? We have a combination, we have back here in the block section, we have what one block looks like. Now here we have multiple different blocks, right? Each one of these represents a different block, but we have an additional column here, or we have additional variable here. So like before, we have block, nonce, and data, right? We have block, nonce, data, but we also have this thing called previous, right? And so this is actually going to be pointing to the previous hash of the last block. So for example, if we go to the last block in this blockchain, it says previous is 00AE8. And if we look at the hash of block number 4, it's 0000AE8. And then we look at its previous, it's 40B9. We have 40B9 and so on, all the way back to our first block, which has previous of just all zeros, right? And so the block with the previous of all zeros is going to be known as the Genesis block. So you've probably heard that before, the Genesis block. It's the first block in the blockchain where the previous hash points to a hash that doesn't actually exist. Now, as you can imagine, kind of the same as how this block worked, how the block, nonce, and data all go through the hashing algorithm. In the blockchain, the block, nonce, data, and previous hash all go through this hashing algorithm to figure out, what the hash is, okay? So if we go to over here, for example, if I type in, Patrick, obviously this is now no longer valid, right? Because this nonce combined with the block, the data, and the previous hash aren't going to solve, our problem of having 4 zeros at the start, right? So I'm going to go ahead and fix that, and that's kind of an easy way to see it being broken. But let's take a look. If I break this block right here, what happens if I break the data in here? If I do like Patrick in here, you can see that both of these are now red. Both of these are now invalid, right? Because the block hashed with the nonce, hashed with the new data, which is my name Patrick, hashed with the previous block, is now a brand new hash, right? And this block is still pointing to this previous hash right here, right? Is pointing to this previous block, and now it is wrong and it is messed up, and now its nonce with this previous hash is also wrong, right? And this is where, when we talk about blockchains being immutable, this is exactly how it's immutable, right? Because if I go back and I change anything, if I just typed A right here, the entire blockchain is now invalidated because none of these are going to have nonces that solve this equation anymore. So this is why blockchains are immutable, is because anytime you change one thing, you ruin the rest of the blockchain, okay? So however though, if an A was here originally, we can go ahead and mine these. We can mine all these, but as you can see, this is going to start getting very computationally expensive because I have to go redo basically the entire blockchain. And the farther and farther down the line you get, the harder and harder it becomes to rehash and redo all these different blockchains here. Now this makes a lot of sense, right? So we have this blockchain. It's really hard to change something in the past, but if we do, we can just go ahead and remine it. Now, if I'm the one who controls the blockchain, right? If I'm the one who controls this, and I want to change something in the past, well, okay, great. All I got to do is change this data here, and then mine each one of these. Obviously, it's going to be very computationally expensive, but it's something that I can do, right? If I'm the one who owns the blockchain. Now, here's where the decentralized nature or the distributed nature really makes it incredibly powerful. So we're going to go to the distributed tab here, which I also refer to as the decentralized tab here. And it's going to show us what a blockchain looks like in a decentralized manner. So we have this exact same initial setup here. We have distributed blockchain. We have our first blockchain, which is kind of exactly as the one from here. But we also have more than one. So we have peer A, peer B, and peer C. And when people are talking about peer-to-peer transactions, they're really talking, this is kind of that concept that they're talking about, right? So we have a number of different peers who are running this blockchain technology. They're all weighted equally, right? Each one of these peers or each one of these nodes, each one of these entities running a blockchain has the exact same power as anybody else, right? So the way that we can tell very easily which blockchain is correct or which ones are correct are by looking at this end hash here, right? Or by looking at where we are in the blockchain. Because again, remember, this hash that this in this last block here is going to encompass all of the blocks from before, right? Because this last hash is going to have the previous hash here, which includes the previous hash here, which this hash includes the previous hash here, so this last hash encompasses everything in here, right? And we can look at the hash of peer C, which is 4 zeros and then E4B. We can look at the latest hash of peer B, which is 4 zeros E4B, and then peer A, which is 4 zeros E4B. So all of these peers, all of these nodes, all of these decentralized, these independent, all these independent users running this blockchain software, they're all matched up. It's very easy for their nodes to look at each other and say, hey, great, we are all matched up. Now, let's say that A decides that something happened on the blockchain that they didn't like and they wanted to go back and change something, right? So let's say they change here. Obviously the rest of their blockchain is invalidated and they have to spend a lot of computational power to catch up to speed. So let's go ahead and humor it. Let's say that they did. They ended up catching up. They ended up mining everything. And now they have a valid blockchain, right? It solves the equation. Awesome. However, in block number 3, there's something new, right? This is here and it shouldn't have been here. This is something that peer A put in by themselves. All that happens now is we look at all of the blockchains that are running the software and we're looking at all the hashes at block number 5. So peer A has this new hash now, 0009BC, but peer B has a different hash, 000E4B, right? So who's right? Is it peer A with their new stuff or is it peer B? Well, that's where the decentralizer comes in because then we can look at peer C and peer C also has E4B. So peer B and peer C both say, hey, peer A, you're wrong, get out, right? And peer A will stop being able to participate in the mining rewards because they have essentially forked the blockchain and started their own little blockchain, right, with their own history because they're the only ones with this piece of data in block 3, whereas peer B and peer C have nothing in there. So that really shows why in these blockchain worlds, in this decentralized world, there really is no centralized entity. Peer A, might have been maliciously motivated to change, this block number 3. However, democracy rules, right? The majority rules in the blockchain. Peer B and peer C both say, hey, that's cute and all, peer A, but you're wrong, right? That's not right. Now, it might be a little abstract to just look at data and, us typing kind of random stuff in here and think, okay, yeah, that's data, right? That makes sense. Just kind of random strings in here doesn't really do anything for us. So if we actually go over to the token section here, this is where everything really starts to make a lot of sense. So we have the exact same setup here with peer A, peer B, peer C, except the difference is instead of having kind of this data section, we have this TX, this transaction section, right? And this represents all the transactions that are happening in this block, right? So we're sending $25 from Darcy to Bingley, $4.27 here, 1922, right? And it's the exact same thing. So all these transactions are going to get hashed in the exact same way that the data is going to get hashed. And this is why it's so powerful, because again, if I want to be malicious, right? If I want to say, hey, I really wanted to give Jane a lot more money from Elizabeth, so I'm peer A, and I go back and I change it to 100. Well, now, not only does my whole blockchain get invalidated because that was so long ago, but I'm not going to match any of these other chains, right? And so my blockchain is going to be excluded from the overall blockchain. So, and let's go ahead and fix this. And it's the same thing. If down here, if I become malicious and I want to send, I want Miss Audrey to have less money, maybe I want to send $1, and I go ahead and mine it. The same thing here. This hash now, this 2A1, is not going to match peer B's hash of BBA, and it's not going to match peer C's hash of BBA as well. So the two of them are going to say, hey, your blockchain is invalid. It's not matching the majority. You're out, right? So that's really how these blockchains work at a low level. And it all goes back to this understanding this hash idea and using it in this very sophisticated manner to kind of cryptographically prove where stuff lies. Now, the way the blockchain works is that instead of random stuff put in this data section, it's actually going to be Solidity code in here, defining ways to interact with different blocks and different protocols that are on chain, or, as we've said before, different smart contracts. Now, the next question that you might be asking is, okay, well, how do I know, how can I be sure that I'm the one, let's say I'm Darcy, right? How can I be sure that Darcy was the one to actually send this money here? How do we know that Darcy sent $25 to Bingley? Well, this is where we get into private keys and public keys, and that's what we're going to go into now. Let's just do a quick recap of what we've learned in this section so far, right? We've learned that Ethereum actually runs on this Kitchak 256, but we used SHA 256 for this demo. It doesn't really matter. We're just talking about hashing algorithms. So again, a hash is a unique fixed length string meant to identify any piece of data. A hash algorithm or a hash function is a function or algorithm that computes any type of data into a unique hash. Mining is going to be the process of finding the solution to the blockchain problem. In our example, the problem was finding a hash that starts with 4 zeros. Nodes get paid for mining different blocks, and the problem is going to be different blockchain to blockchain. A block in a blockchain is basically a combination of a block, nonce, transaction, and a previous hash to create this unique hash for this block. And again, depending on the blockchain implementation, this might have a couple other fields or might have different fields, but this is essentially what's going on. Blockchains are decentralized and distributed because many independent users are going to run this blockchain software, and they will check and they will compare against each other to see which blockchains are acting honestly and which ones are acting maliciously. In the blockchain world, majority rules. The nonce here is the answer used or the number used to get this hash. Now, nonce is kind of an overloaded term. It's actually used for a number of different reasons. In this case, we're using it to solve this problem of getting 4 or 5 zeros at the stop of the hash. However, in Ethereum, it'll also be often used as the number of transactions from a given address. So now we're going to talk a little bit about signing these transactions and private keys and some other cryptography pieces, right? Because in this blockchain demo here, we can see we have all these fantastic transactions, right? All these things went through, but how do we know that it was Darcy who was the one to send $25 to Bingley, right? How do we know that actually happened? And this is where all those pieces that we just learned about in our testnet, in our MetaMask account, are really going to start to come to life here a little bit here. So here we have an example of public and private keys. Okay, at the top we have this private key, right? That was randomly generated. A private key is as it kind of states, is a key that you really want to keep secret because you're going to be using this as kind of your secret password for all your transactions, right? I can really pick any any private key, anything that I want. And with it, this algorithm, they're going to use an algorithm, for Ethereum and Bitcoin, they both use this elliptic curve digital signature algorithm. It's a variant of just a digital signature algorithm, and it's going to create this public key, right? I'm really not going to go at all into kind of this digital signature algorithm, but just know it does use some of these, some of the hash knowledge that we just learned, combined with some other pieces to kind of get this public key here. So I'm not going to go too deep into it, but we have this private key that we create, and we get this public key. Now, this public key, we want everybody to have access to, right? This is, whole world can see this. This private key, we really want it to be private. We don't want people to see this. We're going to use this private key as like a password to quote unquote digitally sign transactions. And then people can verify them with this public key. So let's see what this actually looks like. Let's pick a random key, a more secure key, right? Because the longer it is, the more secure it's going to be. And if we go to signatures now, right? Let's say we have this this message that we want, right? We'd say "Hi world," right? We want this to be the message. What's going to happen is this private key that we've created, we can use to sign this data, right? Remember how in the blockchain demo, we were hashing stuff, right? We're using this SHA-256 hash to get this hash. Well, we're doing something similar, but instead of hashing, we're using this digital signature algorithm to create this message signature. Now, what's really powerful about how this algorithm works is that you can create this message signature with your private key, but somebody else can't derive your private key from the message signature. And that's what makes this really, really powerful. However, if we go to verify using this public key, right? And so this is that 0403. This is that same public key. Using this public key, anybody can verify. Oh, let's go ahead and sign it again. Anybody can verify that this signature is yours, right? So you have a private key just for you, so you can sign things, and a public key so that anybody can verify something, right? So anybody can verify this, and let's say somebody tries to fake a transaction from you. They say, "Hey, this is their transaction." All they have to do is verify that this signature against your public key, and very easily this whole thing turns red because it isn't verified, right? The algorithm says, "Hey, that's wrong." So we can go ahead and take that into transactions in this exact same way. So if I want to send money, if I want to send $400 from, my address to another address, using my private key, I can sign that transaction. And anybody else in the world can then verify this transaction, right? And this is why when people say, hide your keys, protect your keys, this is what we're talking about. In our accounts here, right? If we go to settings, and again, the only reason that I'm showing you guys my mnemonic and my private key is because this is a dumpster account. I'm going to throw this away at the end of this video, or I'm just not going to put any real money in it. But when we look at our MetaMask here, we have this mnemonic phrase which allows us to easily get these different private keys, right? So mnemonic phrase combined with whatever account number will get us a private key. So mnemonic phrase combined with 1, we're going to get this private key. And this is when we look at account details, export private key, password confirm. This is going to be the private key that we're going to use to sign our transactions, right? This, if anybody else gets access to this private key, they then can sign transactions for us, and they can send transactions for us. And that's why we want to keep these private. So it works the exact same way, right? So this is why it's so important to hide your private keys and hide your mnemonics. Now, your Ethereum address is actually a piece of your public key. Now, to get our address in Ethereum, all we have to do is take this public key that we've created with our private key, hash it using that same Ethereum hashing algorithm, and then take the last 20 bytes. And that's how we'll actually derive to our address here. Now, knowing the exact methodology of how to get the address doesn't really matter because it could change blockchain to blockchain and could even change in ETH2. But just know that that is essentially how kind of these addresses are derived, right? There's some derivative of the public key, right? Because the public key is public, And using the public key in kind of any public way is totally fine, but not the private key. So that is how we sign our transactions. Note though, this isn't how we send the transaction. So this is just going to sign it, create a transaction for us to send. We'll learn later on how to send these transactions. Whew, so that was a lot of information there too. Let's do a quick recap. Your public key is derived by using a digital signature algorithm on your private key, right? And you want to keep your private key private at all times because you're going to use your private key to sign transactions. Signing transactions with your private key, you are the only one who can actually do this because you can't get the private key from a message signature. However, using your public key, anybody can very easily verify that a signature that's signed by you is in fact signed by you. In our MetaMask, our private keys are located in this account details section. You just hit show private keys and type in your password, and you'll get your private key here. And the address of your account is derived from this private key, and it's derived from this public key. So if you think about it, your private key creates your public key, which then can create your address. And there's a little barrier here, or a big barrier here, because your private key you want to keep private, and your public key and your address can all be public information.
Now, remember how in our MetaMask, we were able to actually create new accounts. Mine says account 6 because I've created actually a few. But how was it actually creating those accounts? Well, now that we know all this, if we go back to our blockchain demo here, what our MetaMask is doing is essentially taking our mnemonic or that multi-word secret phrase and then just hashing it with some number. So secret phrase +0 gets this, and it'll set this as your private key. And for our account 1, that'll be the private key, or maybe it's +1, the exact algorithm that it's using doesn't matter. But if you want to create a new private key where you just hit this create account button, the way it actually picks this account is by taking this secret phrase and then just changing this number. So if I'm on my MetaMask, I do create account. This right now I'm on account 6 because like I said, I made a whole bunch. If I make account 6, right? It's as if we just did the secret phrase +6 and created this new hash or this new private key and created this new hash, and it uses this to make a private key. And this is why in your MetaMask, if you share that secret phrase, if you share that mnemonic device, they will have access to all the accounts that you ever created. However, if you share your private key, it will just give them access to that single account. Secret phrase has access to all the accounts created in your MetaMask or your wallet. Your private key is access to that single account, and the public key or address, anybody can have access to, and it's cool for anybody to have access to. So when I'm thinking about the security of my MetaMask or my wallet, this is kind of the order that I think of it in. The seed phrase or mnemonic or secret phrase is incredibly important. Protect this at all costs, because if somebody else gets access to this, they will have access to all of your accounts. The second most important is the private key, because if somebody gets access to that, they will get access to a single account. And then your public key or address, which whatever, it's public. Now that we know a little bit more about what's going on underneath the hood of these blockchains, let's go back at our transactions and look at this gas thing again, and we'll look to see what's actually happening here. Gas in particular can be a little bit tricky to wrap your head around. So if you don't get it right away, don't worry. As we go through examples, it'll start to make more sense. So before I was saying, let's just look at this transaction fee bit, which is the cost associated with running this transaction. If I scroll over this on Etherscan, I can see this thing that says block base fee per gas plus max priority fee per gas times the gas used, which might be a little bit confusing here. Let's actually break down what's going on Ethereum with EIP 1559 in place. And again, this is going to be specific to Ethereum, as every blockchain might do it a little bit differently. But if we click to see more, we can see a number of useful values here. We can see gas limit is 21,000 and usage is 21,000. So this transaction used 21,000 gas, and we sent 21,000 gas along with it. Sometimes when sending a transaction, depending on when it's sent and depending on what the specific instructions are, it might actually use way more gas than what you want it to use. So with your transactions, you can actually set a limit. Hey, I don't want to use more than X amount of gas. I don't want to do more than X computational units. And in fact, if we go to our MetaMask and we click send to transfer between accounts again, and we pick, 0.01 ETH or something,
Next, you can actually hit this little button here, go to advanced, and we can actually edit some specifics of this transaction. One of them is going to be the gas limit. We can change this gas limit to maybe 2200, 2300, or more or even less. Since sending Ethereum takes exactly 21,000 gas, MetaMask just defaults to setting it to that. But we also see these other interesting things. We see a priority fee and a max base fee. Let's reject this transaction and let's look back at Etherscan to talk about these. So currently in Ethereum, according to EIP 1559, every transaction on Ethereum comes with something called the base fee. This is the minimum gas price you need to set to include your transaction. And you'll notice that these are priced in something called GWEI. So what is a GWEI? If we come to the site ethconverter.com, and again, there's a link to this in the GitHub repository, we scroll down, we can see WEI, GWEI, and Ether. If I put 1 Ether in here, I can see how much 1 Ether is in terms of GWEI and in terms of WEI. 1 Ether is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 zeros. So that's 1 billion GWEI is going to be 1 Ether. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, and then 18 zeros is a WEI. These are just easier ways of referring to really, really small amounts of Ethereum. So if we look at our gas fees, we see that the base fee is 0.00000004 GWEI. And this obviously would be an even smaller number if this was in units of WEI. So if we take this number and we put it into our calculator, we can see that this is equal to 40 WEI, or 0.00000, a whole bunch of zeros for Ether. The max fee here refers to the maximum gas fee that we're willing to pay for this transaction. And you can actually see that our max fee is a little bit higher than what we actually ended up paying. Our max fee was 2.2132 something something, and the gas price we actually paid was up here. Now your transaction might, of course, be a little bit different. Then additionally, we have a max priority fee. This is going to be the max gas fee that we're willing to pay, plus the max tip that we're willing to give to miners. Now, currently in Ethereum, this base fee ends up getting burnt. And we can see on Etherscan exactly how much is getting burnt here. And if we pull up our calculator again, we can grab this gas fee, multiply it by the amount of gas we used, and we can see that this is indeed how much Ethereum we actually ended up burning. We go back to Ethereum converter, paste it in, we can see that these two numbers are indeed equal. This means whenever you send a transaction, a little bit of Ethereum is removed from circulation forever, or it's considered burnt. So currently in Ethereum, part of your transaction fee actually gets burnt, and then the other part goes directly to miners. So to figure out exactly how much went to miners, we could do this number minus the burnt amount. And this is how much Ethereum was paid to an Ethereum miner for this transaction. You'll see down here, transaction type 2, EIP 1559. This is the EIP 1559 version of these transactions. Like I said, every blockchain is going to have a different fee burning and fee and gas process, and they're all going to be a little bit different. But the sum of it is, blockchains have limited block space for transactions. The gas price that costs for your transaction to be included in one of these blocks changes based off how much demand there is. The base gas fee for Ethereum will go up and down depending on how many people are sending transactions and how many people want to be included in a block. If a ton of people want to be included in a block, that means a ton of gas is obviously going to get burnt. We've left a link to a video in the GitHub repository with this section from this YouTuber who does an amazing job breaking down this EIP 1559 and more about how this gas model actually works. I highly recommend you pause this video and watch that video to understand more. The base fee gets programmatically, algorithmically adjusted to try to target for all the blocks to be 50% full. If they're more than 50% full, this base fee automatically goes up. If they're less than 50% full, this base fee goes down. Now, this is a lot of the basics of how this transaction works, and it can be a little confusing. So let's do a quick refresher of everything in here. There's a unique transaction hash that uniquely identifies this transaction on this blockchain. We can see the status, We can see the block number that it's confirmed on. One other thing we want to look at, if we scroll up, we see block number and block confirmations. This is how many blocks have been mined since this block was included. Like we saw with our blockchain demo, the longer the blockchain gets, the harder it is to tamper with and the more secure it is. Typically, you'll see some processes say they'll only do something after 20 block confirmations, 30 block confirmations, or etc. The reason that they wait for these block confirmations is because they want to make sure that that transaction is actually included. And we can actually see the block that our transaction was included in and all the other transactions with it, different details about how much gas was used, the gas limit, etc. Timestamp is when the transaction happened. We can see from and to, we can see the value, and then we can see the transaction fee, which we see right here is block base fee per gas plus the max priority fee per gas times the gas used. And we see all the details of the gas down here. Gas price is the cost of 1 unit of gas. Gas limit is the max amount of units of gas that we're willing to pay in this transaction. The usage is how many actually got used. The base fee is going to be the base network fee per gas, so 40 Wei per 1 gas used. The max gas is the max gas price we're willing to pay, and max priority is going to be the max gas price plus the tip that we give to miners. And then we can see how much is burnt, and then we see transaction savings, which is the difference between how much was actually used or paid for and then returned. So for example, in this transaction, the gas price we ended up picking was a little less than our max gas price here. So the gas price we ended up using was a little less than our max priority fee here. So we had some savings compared to that. We can also see that this was an EIP 1559 transaction. We can see our nonce here, which was nonce 0 because the transaction that I'm showing is our first nonce. And then of course, we can see the input data. For transactions that are just sending Ethereum, the input data is going to be blank. But you'll see that when we get to smart contracts, the input data is not going to be blank, and it's going to be one of the most important features of these transactions. You'll also notice that there's a state tab. This is an advanced tab, and it shows the different states that are changed based off of this transaction. We're going to ignore this one for now. Now that we know how the blockchain itself works under the hood, let's talk about some blockchain fundamentals. And we actually covered all these topics in a previous Free Code Camp video. So let's go to that. If the first time you listen to this, some of these concepts seem a little bit hard to grasp, don't worry about it. As we continue and as we move on with this course, they'll start to make more sense when you see them used in real examples. I definitely would recommend going back and rewatching and re-listening to the parts that you don't quite get and asking questions in the discussions tab of the GitHub repository.
Awesome. So now that we know all the cryptography pieces and all the little nitty-gritties of how the blockchain actually works and how our signatures work and how everything sticks together, let's talk a little bit about how this works in actuality and what's really going on. Now, for a lot of this, each different blockchain has slightly different algorithms and slightly different metrics and criteria for doing a lot of this stuff. So when we're talking about these specific implementations, keep in mind the exact algorithm might be a little bit different, but the concepts are all still going to be exactly the same. Hashing and a hash function is going to be the same no matter where you look. A decentralized blockchain is going to be the same no matter where you look. How it's actually implemented is going to be a little bit different. Now, traditionally, when you run an application, be it a website or something that connects to some server, you are interacting with a centralized entity. And unlike how we saw with the blockchain with multiple different peers, it's going to be run by a single centralized group. Now, it still could be run on many different servers, but all those servers are still going to be controlled by the same centralized group. Blockchains, as we saw, run on a network of different independent nodes. When we saw peer A, peer B, peer C, those were different examples of different independent users running the blockchain technology on their own node. Now, when I use the term node, I'm usually referring to a single instance of a decentralized system. So when I say a single node, when I'm talking about a blockchain, I'm talking about one of those peer A's, peer B's, peer C's running that blockchain software. I'm talking about one server running this technology. And again, it's this network, it's this combination of these nodes interacting with each other that creates this entire blockchain. What makes these so potent too is that anybody can join the network, and that's why there's decentralized. The barrier to entry is a little bit of hardware requirements, you getting the correct materials to run the software, and then you running the software. Anybody can join these networks and participate, and that's what makes it truly decentralized. In fact, you can go to GitHub right now and run your own Ethereum node in a few seconds. Now, in the traditional world, applications are run by centralized entities. And if that entity goes down, or is maliciously bribed, or decides that they want to shut off, they just can't, because they're the ones that control everything. Blockchains, by contrast, don't have this problem. If one node or one entity that runs several nodes goes down, since there are so many other independent nodes running that it doesn't matter. The blockchain and the system will persist so long as there is at least one node always running. And luckily for us, most of the most popular chains like Bitcoin and Ethereum have thousands and thousands of nodes. And as we showed in our demo, if one node acts maliciously, all the other nodes will ignore that node and kick that out, or even punish it in some systems, because they can easily check everybody else's node and see, okay, this one is out of sync with the majority. And yes, majority rules when it comes to the blockchain. Each blockchain keeps a full list of every transaction and interaction that's happened on that blockchain. And we saw if a node tries to act maliciously, then all their hashes are going to be way out of whack and they're not going to match everybody else. This gives blockchains this incredibly potent immutability trait where nothing can be changed or corrupted. So in essence, we can think of a blockchain as a decentralized database. And with Ethereum, it has an extra additional feature where it also can do computation in a decentralized manner. Now let's talk consensus, proof of work, and proof of stake, because you've probably heard these before and they're really important to how these blockchains actually work. When we went through that blockchain example and we did that mining feature, this is what's known as proof of work. Proof of work and proof of stake fall under this umbrella of consensus. And consensus is a really important topic when it comes to blockchains. Consensus is defined as the mechanism used to reach an agreement on the state or a single value on the blockchain, especially in a decentralized system. I briefly alluded to this consensus mechanism in our blockchain example when I said if one changes something and the other two don't, then majority will rule and kick that one out. This is part of that consensus mechanism. Now, very roughly, a consensus protocol in a blockchain or decentralized system can be broken down into two pieces: a chain selection algorithm and a Sybil resistance mechanism. That mining piece that we were doing, or the proof of work algorithm, is what's known as a Sybil resistance mechanism. And this is what Ethereum and Bitcoin currently use. Please note that depending on when you're watching this, if ETH2 is out, then it's no longer proof of work. Now, proof of work is known as a Sybil resistance mechanism because it defines a way to figure out who is the block author. Which node is going to be the node who did the work to find that mine and be the author of that block, so all the other nodes can verify that it's accurate. Sybil resistance is a blockchain's ability to defend against users creating a large number of pseudo-anonymous identities to gain a disproportionately advantageous influence over said system. And in layman's terms, it's basically a way for a blockchain to defend against somebody making a bunch of fake blockchains so that they can get more and more rewards. Now, there are two types of the Sybil resistance mechanisms that we're going to talk about here, namely proof of work and proof of stake. Let's talk about proof of work a little bit more in depth first. In proof of work, this is Sybil resistant because a single node has to go through a very computationally expensive process called mining, which we demonstrated earlier, to figure out the answer to the blockchain's riddle of finding that correct nonce or whatever the blockchain system has in place. In proof of work, this works because no matter how many pseudo-anonymous accounts you make, each one still has to undergo this very computationally expensive activity of finding the answer to the proof of work problem or the proof of work riddle, which again, in our demonstration, it was finding a nonce with that first 4 zeros. But again, each blockchain might change the riddle or change the problem to be a little bit different. In fact, some of these blockchains make this riddle intentionally hard or intentionally easy to change what's called the block time. The block time is how long it takes between blocks being published, and it's proportional to how hard these algorithms are. So these problems actually can change depending on how long they want the block time to be. If a system wants the block time to be very, very long, they just make the problem very, very hard. If they want it to be very short, they make the problem a lot easier. We'll talk about Sybil attacks in a little bit and how they can affect the system. But with proof of work, it's a verifiable way to figure out who the block author is and be Sybil resistant. Now, you need to combine this with a chain selection rule, create this consensus. Now, there's some consensus protocols that have more features, but very, very roughly, these are the two pieces that we're going to look at. The second piece is going to be a chain selection rule. How do we know which blockchain is actually the real blockchain and the true blockchain. Now, on Bitcoin and Ethereum, they both use a form of consensus called Nakamoto consensus. And this is a combination of proof of work and longest chain rule. The decentralized network decides that whichever blockchain has the longest chain or the most number of blocks on it is going to be the chain that they use. This makes a lot of sense because every additional block that a chain is behind, it's going to take more and more computation for it to come up. That's why when we saw in our transaction, we actually saw confirmations. The number of confirmations is the number of additional blocks added on after our transaction went through in a block. So if we see confirmations as 2, it means that the block that our transaction was in has 2 blocks ahead of it in the longest chain. Now, I do want to point out that a lot of people use proof of work as a consensus protocol, and I do want to say that this is a little bit inaccurate, but sometimes people use it interchangeably. Proof of work is a piece of the overall consensus protocol, which in Bitcoin and Ethereum 1's current case is Nakamoto consensus. Nakamoto consensus is a combination of proof of work and this longest chain rule, both equally and very, very important. Now, proof of work also tells us where these transaction fees and these block rewards go to. Remember how when we made this transaction, we had to talk about gas and a transaction fee. So who's getting paid? Who is getting this transaction? And this transaction fee is going to the miners or the validators. In a proof of work network, they're called miners, and in the proof of stake network, they're called validators. They are a little bit different, and we'll get into that when we talk about proof of stake. In this proof of work system, all these nodes are competing against each other to find the answer to the blockchain riddle. Remember, in our example, it was to find a hash that has 4 zeros at the start. And again, depending on the blockchain implementation, that riddle is going to be a little bit different. But all the nodes are trying as many as possible to try to get this answer first. Why? Because the first node to figure out the answer to the blockchain riddle is going to get that transaction fee. They're going to get paid from that. Now, when a node gets paid, they actually get paid in 2 different ways. One is going to be with a transaction fee, and another piece is going to be the block reward. Remember how we talked about alternating the gas price or the GUE on our transaction? Well, that's the transaction fee that we're going to pay to these blockchain nodes for including our transaction. The block reward is given to these nodes from the protocol, from the blockchain itself. You've probably heard of the Bitcoin halving before. The halving is referring to this block reward getting cut in half, and it's supposed to be cut in half roughly every 4 years. This block reward increases the circulating amount of whatever cryptocurrency that is being rewarded. For example, on Ethereum, the block reward is giving out Ethereum, and on Bitcoin, the block reward is giving out Bitcoin. So these nodes are competing against each other to be the first one to find this transaction, to be the first one to find the answer to this problem, so that they can be the ones to win both this block reward and your transaction fee. Some blockchains, like Bitcoin, for example, have a set time when they're no longer going to give out block rewards, and the miners or the nodes are only going to get paid from transaction fees. Now, this gas fee, again, is paid by whoever initialized the transaction. When we got our funds from the faucet, there was some server and somebody else was paying the transaction fee for us. However, when we sent Ether from one account to another, our first account actually paid some transaction fee to send that Ether. In proof of stake, there's also a gas fee, but it's paid out to validators instead of miners, and we'll talk about that in a little bit. Now let's talk about 2 types of attacks that can happen in these blockchain worlds. Let's talk about the first one being the Sybil attack. The Sybil attack is when a user creates a whole bunch of pseudo-anonymous accounts to try to influence a network. Now, obviously on Bitcoin and Ethereum, this is really, really difficult because the user needs to do all this work in proof of work or have a ton of collateral in proof of stake, which again, we'll talk about in a bit. The other more prevalent attack is what's known as a 51% attack. Now, as we saw as part of our consensus protocol, these blockchains are going to agree that the longest chain is the one that they're going to go with, so long as it matches up with 51% of the rest of the network. This means that if you have the longest chain and you have more than 51% of the rest of the network, you can do what's called a fork in the network and bring the network onto your now longest chain. Now, Sybil attacks obviously are when a single node or a single entity tries to affect the decentrality of the network by pretending to be multiple different people, although they're just the same person or entity. And like I said, it's really difficult to do in proof of work and proof of stake. So you can see now that blockchains are very democratic. Whichever blockchain has the most buy-in and is the longest is the blockchain that the whole system is going to corroborate. When nodes produce a new block and add it to the longest chain, the other nodes will follow this longest chain that the rest of the network is agreeing with, add those blocks to their chain, and follow up. So very small reorganizations are actually pretty common when a blockchain picks a block from a different longest chain, puts it on, and then has to swap it out for another block and continue with a different blockchain. However, if a group of nodes had enough nodes or enough power, they could essentially be 51% of the network and influence the network in whatever direction that they wanted. This is what's known as a 51% attack, and it's happened on blockchains like Ethereum Classic, which is not Ethereum. This is why the bigger a blockchain is, the more decentralized and the more secure it becomes. So after you watch this video and you become a blockchain engineering expert, I definitely recommend you run a node as well, because you are going to increase the security of the network as a whole by running a node. So proof of work is fantastic because it allows us to very easily protect against these Sybil attacks and keep our blockchains decentralized and secure. However, it has some drawbacks as well. Proof of work costs a lot of electricity because every single node is running as fast as they can to win this race to get the rewards. This leads to, obviously, an environmental impact. Now, since proof of work and Nakamoto consensus, a lot of other protocols have taken this idea and gone in a different direction with a different Sybil resistance protocol. A lot of them with the intention to be a lot more environmentally friendly. And the most popular one right now is proof of stake. There are some chains that are already using this proof of stake protocol and that are live and thriving. Some of them are like Avalanche Solana, Polygon, Polkadot. So let's talk about proof of stake now. Again, this is a different Sybil resistance mechanism. Instead of solving this difficult problem, proof of stake nodes put up some collateral that they're going to behave honestly, aka they stake. In the example of Ethereum 2, nodes put up some Ethereum as a stake that they're going to behave honestly in the network. If they misbehave in the network, they are going to be slashed or removed some of their stake. Obviously, this is a very good Sybil resistance mechanism because if you try to create a whole bunch of anonymous accounts, then each one of those accounts, you have to put up some stake. And if you misbehave, you're going to run the risk of losing all the money that you put up as collateral. In this system, miners are actually called validators because they're no longer binding anything. They're actually just validating other nodes. Now, unlike proof of work, which every node is racing to be the first one to find the block, in proof of stake, nodes are actually randomly chosen to propose the new block. And then the rest of the validators will validate if that node has proposed the block honestly. As we saw with our cryptography lesson, it's usually very easy for other nodes to verify if a proposal or a transaction is honest. Now, proof of stake obviously has some pros and cons as well. Pros are that, again, it is a great Sybil resistance mechanism and a great way to figure out who the author of a block should be. The other pros are that it's way less computationally expensive to figure out the new block, because instead of every single node on the network trying to do this, only one node needs to do this. And then the rest of the nodes just need to validate it. The cons are that it's usually considered a slightly less decentralized network due to the upfront staking costs it costs to participate. Now, this gets into a little bit of a philosophical battle on how decentralized is decentralized enough, and I think that's up to the community to decide. And as we progress, I think we'll learn more and more about how decentralized is decentralized enough. The general consensus amongst blockchain engineers, though, is that proof of stake is very, very decentralized and very secure. Now, there's another term that might be the first time you heard it, a layer 1. We're going to talk about layer 1s and layer 2s in terms of scalability really quickly as well. A layer 1 refers to any base layer blockchain implementation. Bitcoin's a layer 1, Ethereum's a layer 1, Avalanche is a layer 1. These are the base layer blockchain solutions. A layer 2 is any application that is added on top of a layer 1, added on top of a blockchain. Some examples of layer 2s are going to be Chainlink, Arbitrum, or Optimism. Arbitrum and Optimism are very interesting because they are layer 2s that also look to solve this scalability issue. Arbitrum and Optimism are what's known as rollups, and they roll up their transactions into a layer 1, like Ethereum. We're not going to go too deep into rollups and how they actually work, but all you really need to know is that they solve some of the scalability issues by being another blockchain that people can make transactions on, still on kind of this base Ethereum layer. Now, they're different from side chains because side chains derive their security from their own protocols. Rollups derive their security from the base layers. So Arbitrum and Optimism, for example, is going to be just about as secure as Ethereum. There's some fantastic guides in there that go a little bit deeper into rollups, and I've left a link in the description for you. All right, so we just talked about a lot of stuff. So let's do a quick recap before moving on. Sybil attacks are prevented due to protocols like proof of work and proof of stake. 51% attacks grow increasingly harder with the size of blockchain, so you should run a node. Consensus is the mechanism that allows a blockchain to agree upon what the state of the blockchain is. Sharding and rollups are solutions to scalability issues on layer 1s. A layer 1 is any base blockchain implementation, like Bitcoin or Ethereum. A blockchain scalability problem is that there's not always enough block space for the amount of transactions that want to get in them. This leads to very high gas prices. And again, gas prices are how much it costs to interact with a blockchain. Whew.
So that's it for the blockchain basics and the blockchain explainers. With just this information, you now can go off into the world and start working with blockchains and interacting with blockchains with at least some level of knowledge as to what's going on. You should be incredibly proud of yourself for just making it this far. Definitely be sure to give yourself a pat on the back and a round of applause. Now that we've gotten a lot of the basics and the fundamentals out of the way, let's start jumping into the coding aspect. This is where you're going to learn how to actually build these smart contracts, how to build these trust minimized agreements in these blockchains and in these smart contract platforms. This next section, this Solidity Basics, the Solidity Fundamentals section, will give you all the skills to start actually coding Solidity and understanding how these smart contracts work underneath the hood. So at this point, absolutely give yourself a high five, maybe say hi in the GitHub discussions, maybe say hi in the community, on Twitter, on Reddit, etc., and be proud of just making it this far. The journey has really only just begun, but you've already learned so much. Let's begin the next section and let's jump into the code.